Swayam Prabha. Digital India. Educated India.
Good afternoon friends. So, we are into the second lecture of our week number 11, where we are talking about reactor safety and security. In the previous lecture of this module, we are mostly in a storytelling mode basically, where I just talked about a few major nuclear incidents that has happened worldwide, like of course the Hiroshima incident, and then a couple of very important, or I should say very significant nuclear accidents that has happened at the 3 Mile Islands and Chernobyl. And taking that into account, whatever lessons we learned from those accidents, starting from there, today we are going to discuss about different kind of safety aspects or safety considerations which are integrated in the design of a nuclear power station. So, just a quick recap of the previous lecture. We started with the biological effects of radiation, which actually was the topic of the previous week, but still I gave a brief summary of that, particularly stressing upon the genetic mutation caused by radiation, because the effect of radiation, as I have mentioned, the effect of any nuclear accident is not just an instantaneous one, rather can be very long, can have very long term effect, because the radioactive nuclei or radioactive isotopes which are released to the environment as a result of a nuclear accident can have very long half life, and therefore, they can keep on decaying while emitting beta and gamma rays to the surrounding over a very long period. Very long may refer to a few years, a few 100 years, or maybe a few million years, and that is why the consequences of a nuclear power accident or an accident in a nuclear power plant can be very far reaching, and we have to be very mindful about possible consequences, particularly the effect the radiation can cause at the prenatal stage, that is to the fetus, can have far reaching effect, and that is why we mentioned about the genetic mutation in the previous lecture. Then the post Hiroshima experience, what are the experience that we gained or the nuclear industry gained from that catastrophe. Then we discussed about the 3 Mile Island nuclear accident, which happened in 1979 in a nuclear power plant at United States, a much bigger scale accident which happened in 1986 in Chernobyl of former Soviet Union, something which is termed as the biggest man-made accident ever to happen in a power station. The Chernobyl accident is regarded as the largest scale level accident that can happen to a nuclear power plant, and it has very far reaching implication both on the nuclear industry and also on the corresponding research. Like we have seen yesterday, following the incidents of TMI and particularly Chernobyl, there is a huge dip in the installation of new nuclear power plants. Actually, in United States and also globally, hardly any nuclear power plant came up during the period of 1980 to 1998 2000, and it was almost in a stalemate kind of situation, as the global nuclear power production capacity remained almost same over the span of 15-20 years. But then with the advent of the generation 3 and generation 4 concepts with much higher level of security aspects, newer nuclear plants again have started to come up. But still the radiation effect, which now it is about, we are more than 30 years from the Chernobyl incident, and so we have quite a decent level of data to analyze the post effect of Chernobyl. Like we have seen the bridge of death or Pripyat yesterday. It was a small town located just about 3 miles away from the Chernobyl power station, and when the accident happened, people ran to that bridge to see exactly what happened, and there are lots of people standing on that bridge observing the fire and whatever was happening in that plant, and unfortunately they are unaware that they are in the direct path of the radiation that is coming from the plant. So lots of them suffered from strong radioactive disease, radioactive syndrome, acute radioactive syndrome, something which is called, but there is no proper data about what is the exact effect. At least, but still, as we have covered 30 years, we have some more data, and all those informations are regularly getting added to the database, thereby strengthening the research related to the security aspects. And by analyzing those lessons from TMI and Chernobyl, and also I must add, which I have not discussed yesterday, the very recent incident at Fukushima, the Daiichi power station. Culminating all these experiences, we have got newer safety guidelines, and from this the fundamental safety objective was identified as to protect people and the environment from harmful effects of ionizing radiation. That is the pioneering objective of this entire module, to identify options which will isolate the ionizing radiation coming out from the fission products, particularly from the human being and also to the environment. That is, no way those fission products are coming in free contact with the environment or to the human being. That is what we are trying to ensure. And the methodology that is followed, the approach that is followed to attain that objective is known as defense in depth. It is a basic design philosophy which is followed globally. Different countries have their own methodologies, but the levels or the procedures are more or less similar, and all those procedures are the sequence of events which are followed. That is what is called the defense in depth. It always refers to multiple safety systems. Basically, it comprises of several layers of security. All those layers are independent and subsequent in nature, and the objective is to supplement the natural features of the core. Key aspects of this approach can be three factors. First is prevention. The high quality design and construction must be ensured so that the reactor operates with a high degree of reliability. The prevention of accidents is through intrinsic design features and stresses on quality control, redundancy testing, inspection, and fail safe design. Couple of those terms like this, redundancy or fail safe, we shall be seeing shortly in this lecture itself. But the meaning of this particular term refers to, we have to ensure high quality design and construction so that all possible types of reactions possible types of accidents or incidents, at least those which we can foresee, can be killed at the design level itself. And also we have to ensure that the equipments, we install equipments which are capable of preventing operational disturbances or human failures, and also will not allow any kind of small disturbance or small error into a much bigger issue. Before that only it will be able to either subside the event or make the authorities aware about what may happen in next few minutes to come, or in the next period to come. The second aspect of defense in depth is monitoring, comprehensive monitoring and regular testing to detect equipment or operator failures. Particularly as time goes on, as the aging effect starts to become dominant, it is very much possible that different parts of the plants may develop newer cracks, newer effects of the wear and tear. So, and also the equipments, as they become old, many equipments may become less effective, may develop a larger threshold kind of margin, and that is why the operators should ensure continuous monitoring in order to avoid any such kind of oversight, and they must ensure that all the equipments are in perfect operating condition and are capable of giving the proper signal. Like we have seen yesterday while discussing about the Chernobyl incident, it was a valve which was stuck, but the signal that never reached the operator, or rather when there was a light which was blinking on the main instrumentation panel or on the main control panel, which never indicated that the valve was actually stuck and it has not been closed. So, the operator was not able to discover it immediately, and which led to the following catastrophe. at the 3 Mile Island. But continuous monitoring is something by virtue of which we can avoid such kind of situations. And the third aspect of defense in depth, in short, this is also quite commonly referred as DID. So, the third aspect of this DID refers to redundant and diverse systems to control damage to the fuel and prevent subsequent radioactive releases. This term redundant and diverse we shall be discussing, but in short it refers to we need to have systems which are able to control damage to the fuel and prevent subsequent radioactive release, and also we must have provision to confine the effect of severe fuel damage or any other problem within the plant itself. So, these are the three key aspects based on which this entire philosophy of defense in depth revolves around prevention, monitoring and mitigating action. In nuclear power plant, multiple and successive physical barriers are provided as a part of this DID, which are able to, or which theoretically should be able to prevent the leakage of any kind of radioactive effect to the surrounding. And the layers, the subsequent layers of security or protection are arranged such that the failure of one layer should be mitigated by the next one by virtue of its design features itself. So, each layer has their own design features and they are subsequently strengthened to have so that each layer can serve one specific purpose. The safety provisions include series of physical barriers between the radioactive reactor core and the environment. There are generally 4 levels of barriers in conventional reactor. The first barrier, the solid ceramic fuel pellet itself. Generally, the fuel pellets are arranged in some kind of matrix. Like suppose if we are having, this is not the correct way. If suppose you are thinking about fuel pins with circular cross sections, you will always find that the fuel pins are generally arranged in a matrix like this, somewhat like this. This is one layer, then we can have several other layers around this. Number of fuel rods in each layer of course will vary, so that we have some fuel rods arranged in one circle, then another set of fuel layers arranged in another circle where the center is similar, but the diameter is larger. Then we can have generally have 3 such kind of circles which are and number of fuel rod keeps on increasing as we go to circles of larger radius. And now, once these circles which are formed of the fissionable fuel, as they participate in the radioactive reaction, so it produces fission products, and this fuel pellets or these fuel pins are arranged such that the radioactive fission products, they are most likely to be bounded within these intermediate zones only, or maybe just get stacked up somewhere here. So, the first level of barrier is provided by the fuel pellet itself. It may also happen if you are talking about an individual fuel pellet, all the fissionable elements inside this particular fuel pellet or fuel rod are not participating in fission reaction simultaneously. It may happen only the inner core participating in fission reaction, and therefore, all the corresponding fission products they get stuck inside this single fission elements or single fuel rod itself. This is what refers to as the first barrier. The ceramic fuel rods are the one most important contributor as a part of this first barrier. Next question is, what can be the second barrier then? After the fuel pellet, what we have, or after the fuel, that is the cladding. So, and while studying the cladding, we have learned that one of the functions of cladding is to prevent the release of radioactive fission products to the surrounding or to the coolant stream. So, cladding provides the second level of barrier. Cladding can be made of zircaloy or magnox, or in certain situation maybe of stainless steel. This being a strong and generally non-permeable kind of metallic sheets, they are able to prevent the leakage of fission fragments quite efficiently. Third refers to the pressure vessel or pressure tube. Pressure vessel is pertinent to light water reactors like PWR or BWR, where pressure tube type design, I hope you remember, PHWR is something that is a pressure tube type design, and the corresponding walls for this pressure vessel or pressure tube can be very thick. Like the pressure vessels conventionally have very thick steel wall having thickness of the level of 30 centimeter. So, that is the third level of barrier which prevents the leakage of those fission products. And finally, the containment structure generally made of reinforced concrete which can be as much as 1 meter thickness. This is a typical diagram which shows all these 4 barriers. This is the fuel rod. So, the crystal fuel structure inside the fuel rod itself forms the first barrier. Then we have this second cladding which is basically a jacket inside the around the fuel. Then we have the third barrier, the fuel rods are placed inside the pressure vessel as per this diagram, and then this entire containment structure outside, this black one, this is the containment structure which is the fourth barrier. Of course, all these barriers or protection layers have their own dedicated systems to protect the integrity of these barriers, and barriers are supported by different retaining functions like water layers, pressure differences, filters in ventilation systems, etc., but main objectives are being performed by these barriers. Now, despite making all these efforts, it is very much possible that still some fission products may come out of the reactor, or because of some other reasons there may be accidents. And from whatever experience that we have about the nuclear reactors, now we are in a position to anticipate the types of accidents which may happen in certain power stations, and making use of those knowledge, reliable protection devices are provided to prevent or minimize the effect of any such incident. And conventionally, modern nuclear power plant employs, along with those 4 barriers that we have discussed, they also employs 5 layers of protection. First protection, of course, initially the barriers that we have seen, if we just go to the center of this particular picture, the first barrier is provided by the fuel matrix, then is the cladding, and third is the primary circuit boundary. But before it encounters the fourth one, we can install the first level of protection, and the objective of this first level, which is given by this white line here or this white layer, the objective is just immediate, just to protect the release of or protect the reactor against any kind of accident scenario. So, the objective of first level as written here is the prevention of deviation from the normal operating conditions. So, the first level tries to retain the reactor in the normal operating condition, which invariably is a critical one. Even whenever there is some change, say in the operating conditions, maybe small change, maybe a large change, this first level should try to get the system back to its original position. The second level, which is given by this particular layer here, it refers to the control of abnormal operation. If somehow the first level fails, then the reactor can't sustain the normal operation, then it will go to the abnormal operation. Prevention of deviation from the normal operation, or just ensure that the normal operation is always running, is the job performed by the first layer. And the second layer, accidentally if the nuclear product or has at all been formed, then this second layer ensures the control of abnormal operation. And then a very important one, third layer, which tries to control the accidents in the design level itself. Again, from our experience, we can foresee quite a few different types of nuclear accidents. So, we can provide enough arrangement in the second level, so that even if there is may not be an accident, but even if there is small kind of deviation, or the system has deviated a bit from the normal condition, that can be tackled here. In the first level, it tries to get the system maintain the normal condition always. Like if there is, say, system is running as a critical one, a critical reactor, and now there is small, because of some change in any of the operating conditions, the system becomes supercritical. Say its reactivity has become positive by a small margin, then the first level ensures that the reactivity gets back to the normal condition, that it gets back to 0, and the reactors continues to operate as the critical one. But if somehow the first level fails, then comes the role of this second level. Now it is no more an abnormal operation, it is rather abnormal, because the system is running as a supercritical one. So, it has to provide provisions of getting the system back to the normal condition. The third level where we have the accidents coming in. From our experience, we already have idea what are the different kinds of accidents that we may find in a nuclear power plant. So, when both the first and second level fails, it leads to an accident, and that is why the third level has provisions of controlling those accidents and get the system back to the normal condition again, or at least get it back to such situation, so that the second level can become active again and can take care of the rest of the situation. So, in this diagram, the 4 level of barriers or 4 physical barriers that we have talked about, you can see this is the fuel matrix, and then we have the cladding, then the primary circuit boundary, and here we have the fourth one, that is the confinement, which does not allow the radiation to come out. But after the third level, when even if the third level also fails, then we have a real accident situation, and now we need to go for some kind of accident management technique. That is where the fourth level is. It is the outermost layer of protection in a nuclear power plant, which looks at the which looks at the accident management, including confinement protection. And finally, the fifth level, which is which refers to a very severe accident, which where even none of the previous 4 layers are able to take care of. Then offsite emergency response system needs to be activated to prevent the spreading of radioactivity far away from the plant itself, preferably limit that within the plant itself. So, we conventionally can have 5 layers of protection in defensive depth. The first layer of protection refers to prevention of deviation from normal operation. The installation must be endowed with excellent intrinsic resistance to its own failures or specified hazards in order to reduce the risk of failure. So, in the first level itself, we have to provide options so that the system can always get back to small deviation or small amount of failures. This implies that an exhaustive study as possible of its normal and foreseeable operating condition be conducted to determine the response of a system against defined kind of scenarios, such as the worst mechanical thermal pressure stresses the system may encounter because of environmental issues, because of its layout for each major subsystem structure or component. It also considers the normal operating transients and the various shutdown situations, various disturbances or hazards deriving from a source external to the plant. The seismic waves can also need to be considered if that at all becomes relevant to the corresponding location. And the extreme meteorological conditions expressed as wind speed, weight of snow, maximum water pressure, wave temperature range, etc. So, considering all these aspects, we design the level 1, so that the system is able to continue or maintain its critical condition, or at least the desired operating condition. The installation components can then be designed, constructed, installed, checked, tested and operated by following the clearly defined and quality rules, which while allowing adequate margins with regard to specific limits at all times to undergo and correct behavior of the installation. Adequate margin must be provided with regard to specific limits at all times to undergo correct behavior of the installation. The margins are such that the system is designed to deal with abnormal situations need not be actuated on an overday basis or on a daily basis. Man-machine interface provisions and time allowances for manual intervention. In the second level, it must be prevented from straying beyond the authorized operating condition. The temperature, pressure and nuclear and thermal power control systems are installed to prevent excessive incident development without interfering with proper plans. A stable core with high thermal inertia is more likely to hold the installation within the authorized limit. Like high thermal inertia refers to with the given heat load, the temperature rise of the system will be smaller. And once we can ensure that, then the system can limit its temperature change within a very short range, and also if the core itself is stable, then the system will not rush. Core itself is stable, then the system will last, and this will be able to get back to the abnormal condition. The systems for measuring the radioactivity levels for certain fluids and the atmosphere must also be installed. An emergency shutdown system shall be capable of rapidly arresting any undesirable phenomena. Finally, a periodic equipment surveillance program, like we had in the previous case also in level 1, Equipment services surveillance program are including periodic weld inspection like crack and leak detection, routing system testing, etc. So, by virtue of by applying these methods, we can control, we at least try to control the abnormal operation. But when both level 1 and 2 fails, we come to level 3, which must control the accidents at design level. A complete series of accidents and incidents are postulated while designing a nuclear power plant, and taking the corresponding data, only the final designs are drawn. The design and installation of safety systems having no function under normal operating conditions, that is the safety systems that we are going to install under this level 3, they may not be functional at all during a normal power operation. Automatic startup of these systems are essential, and human intervention should be required after a time gap, which will allow a careful consideration diagnosis to whether diagnosis should be reached. The core structure integrity must remain unaffected throughout, and the choice of incident and accident must be named from the beginning of the design phase of a project. Such engineer safeguard must be integrated perfectly with the overall installation design. So, the equipment which or installations which comes under this third layer, they should be able to subside all those design level accidents, that is the accidents which we can foresee, and therefore, their concerned effect has been considered while designing the system itself. Fourth is accident management, including confinement protection. This is more like the final result or final barrier which will not allow the release of radioactivity to the surrounding. Following TMI and Chernobyl experience, it was decided to consider cases of multiple failure, and more generally the means required to contend with plant situation which bypass the first 3 levels of protection. Such situation can lead to core meltdown and consequently to even higher release rate. So, to counter that, we need to have appropriate procedure and equipment to withstand additional scenarios corresponding to multiple failures. Complementary measures aimed to prevent core meltdown, endeavor to limit radioactive release due to any serious occurrences, and to gain time to arrange for protective measures for the populations in the vicinity of the site, and where the role of the authority also comes into play, because it is not possible for the plant authority to evacuate a site or to move people from a particular location, but only the local governmental authorities or maybe the governmental bodies can only evacuate a particular location. Maintaining the confinement function under the best possible condition. And first is off-site emergency response. It refers to when all the 4 levels has failed. So, radioactivity has started to go outside the reaction zone, and then we have the role of this level 5 population protection measures. So, the public authorities can help in evacuation of the local site, confinement indoors with doors and windows closed, distribution of stable iodine tablets. It can also instruct the restriction on consumption and selling of certain foodstuffs which can get radioactive, which can become radioactive very quickly. These 4 factors, that is evacuation, confinement, distribution of iodine tablets and restrictions, are together known as external emergency planning. But there can be long term effects as well, or long term planning I should say, like checking the long term consumption and marketing of contaminated foodstuffs, and periodical training deals to ensure adequate preparedness. These are the all 5 tasks put together. Expected during the lifetime of a plant, we can be those events which are expected during the lifetime of a plant. It falls under the level 1 category, and plant can contribute to normal operation, and when it falls during in the faulty zone, it comes under level 2 category, which also allows operational contribution. Second, that is the third level, is very rare and unlikely event. It happens through the safety systems, or it is mitigated by using the safety systems and accident protections. Extremely rare event, the level 4 event, indicates or results in melting of the core material, and frequency of extremely large or early protective measures like limited in the area and time need to be provided, because these are long term effects, falls under level 4, and enough safety features need to be ensured. And finally, the emergency planning, which suits the level 5, it leads to significant release of radioactivity to the surrounding areas and mitigation of radiological impact is generally the objective of this particular level, and drastic protective measures are essential. Now, the safety functions. All the safety features that we install or insist in a plan, they generally falls under three categories, or there generally are three major objectives. One is the control of reactivity. So, whenever there is a change in reactivity, the safety feature should get it back to the desired level immediately, otherwise the reactor will just because of its multiplication factor, it will immediately grow or decay quick. Next, removal of heat from the fuel rods. The rate at which the fission heat are getting produced inside the reactor, at the same rate heat must be removed, because even if there is some loss in the coolant side, which results in smaller amount of coolant flow, immediately there will be immediate increase in the temperature of the temperature level of the coolant than desired, and that can quickly lead to the overheating of the entire reactor core. And finally, the confinement of the radioactive materials and mitigation of releases. To attain all these fundamental safety features, the structure, systems and components which are together known as SSC, that separately or together acts with the, and accordingly the equipments are classified based on the importance of safety, and or rather I should say the equipments which are required to ensure the safety, that is which has relation with any of these three of safety functions, and equipments which are not at all related to safety. Safety systems must ensure that the safe shutdown of the core, residual heat removal from the core, and the consequences of anticipated operational occurrences and design based accidents are taken care of. Here I would like to quickly mention about this residual heat removal. Any amount of heat generation in the reactor that needs to remove, that is true for coal based thermal power plant as well, but there when the coal is burning, we have the energy available and the coolant needs to take that energy, but once the coal has burned, then there is no energy potential available. But that is not true for the nuclear. Like when uranium undergoes fission, it releases large amount of energy, but the products of the fission, they can also be radioactive in nature, and therefore depending upon their respective half lives, it can keep on releasing energy over a very long period of time. That is that's why the energy that is released because of the action of prompt neutrons, that is definitely important, but from safety point of view, the energy released because of the action of the delayed neutrons are much more important, because that is something that is led to this decay heat or residual heat. Now, to have the safety function for control of reactivity, we need to have ensured that the reactivity is limited in the reactor core and also in the fuel storage plant. The thermal power is kept within safe margin, and the damage to the fuel elements must be prevented. It also ensures safe shutdown of the reactor whenever that is desired. So, to attain that, we need to provide effective and reliable controllers and scram function, whereas there can be secondary safety shutdown mechanism also, like injecting boron. If we want to have a very quick shutdown of BWRs, then we can inject large quantity of boron, which can because of its high neutron absorption cross section, it can eat up all the available neutrons. Whereas when we are talking about the heat removal, then the coolant level and flow must be maintained inside the reactor, because any decrease in the flow rate will just as I have mentioned will result in overheating of the plant. The heat sink for residual heat removal should be very much reliable. The heat transport system should be very reliable, that is particularly in boiling water reactors where there is phase change involved, then we must ensure that the operation is limited in the nuclear boiling zone. The reactor is never able to go into the DNB, that is departure from nuclear boiling or flame boiling zone, which can lead to, particularly following the critical heat flux, there will be a subsequent, or I should say substantial decrease in the heat transfer coefficient. So, the heat transfer system must be reliable to ensure the absence of this DNB in BWRs. These functions can be achieved by active recirculation and natural circulation, safety injections and heat removal systems. Like in this particular context, I would like to mention about what happened in this Fukushima power stations. Fukushima power stations, of course, it has its own the Daiichi power stations, basically it has its own issues. It was a very old plant running for more than 40 years, and therefore all the safety measures were not the most advanced one, but still the accident that happened, that was the result of some kind of misfortune for them, because you know that the tsunami has struck that time, just before the accident happened, Japan was struck by tsunami, and because of that tsunami, power grid that failed. So, there was no power available in the reactor, or I should say in the nuclear power plant, and because there was no power available. So, the coolant circulation pump, coolant recirculation pump, that stopped working, and so there was no coolant that was flowing through the reactor core, and hence, but the reactor core, despite all the effort, it continues to produce fission heat, and they were not able to provide and arrange for any additional power. They had some kind of backup generator or diesel generators. Unfortunately, because of the tsunami, those also went underwater, and they are not able to start the pump. As they didn't had any kind of natural circulation kind of background, such kind of passive mechanism they didn't had. So, that lead to LOCA, that is loss of coolant accident. No coolant were there in the plant, and hence it led to the meltdown of the entire reactor core. That is why the newer generation 3 onwards, they are ensuring this passive recirculation systems employing natural circulation, where even in the absence of any kind of prime movers, any kind of electrical sources, the fluid will always be flowing using the buoyancy force. So, the confinement of radioactivity generally refers to, first we have to close the all potential release path like corrosion, wear and tear, the any kind of stress load. Shield must be provided against direct radiation. Designs, material fabrication, dimensioning with high safety margin, and any kind of all kind of recurrent testing, aging management, preventive maintenance, etc. should be done. And finally, isolation equipment. Okay, we also can have additional retention functions like filters, water layers, etc., which can lead to the confinement of reactivity. And shielding material, of course, has to be there. There are several levels of shields which are provided inside around the reactor, like made of concrete. We can have water layers. You know, water has a reasonably high neutron absorption cross section, so it can absorb neutron, thereby avoiding or providing a way of reducing the reactivity inside the core. These are the fundamental 3 characteristics that I mentioned. First, and the 3 aspects of DID: possibility of rapid power excursion in a core. It should be controlled. We should have control of the reactivity and reactor shutdown functions, and other 2 corresponds to the other functions that I have just mentioned. This is the schematic view of one power station where we have several passive safety systems installed. Like we have this safety injection system, then we have this confinement spray system. These are additional system. This is also a confinement spray here, which is coming from this passive heat removal system. So, using this sprays and some other means, I can provide other means, the safety, these 5 layers of safety are ensured. You can see this is another diagram which has implemented fully passive safety systems. It was a natural circulation, and also there are quite a few others fully passive safety systems. Next is the fail-safe design. This term came earlier. So, fail-safe refers to the instruments that we are providing for safety and for ensuring safety. In case of failure, the system must act, or it has the maximum possibility of functioning properly. It should not fail, otherwise there will be catastrophe, because we are dependent on those kind of safety equipments to ensure the maximum probability of functioning. Like you can see this diagram, this is for control rods. These are a normal operating condition. Control rods are nearly taken out of the reactor, they are completely removed, and they are held in this position using some kind of electrical drive. Now, if there is some kind of scram situation, that is we have to suddenly close this reactor core, then we have to deactivate this electrical drive, and then only using some kind of other means we can get this control. We can completely using during scram, we can insert the control rods using these electrical drives, but also we can make use of the gravitational force. Like in this design, control rods are located at the upper position of this reactor shell, and therefore, if we just allow them under gravity, they will fall down till the maximum lowest possible position, thereby allowing the scram. So, we are making use of a natural phenomenon, it is gravity, and hence that is some kind of fail safe design. The recirculation using natural circulation is also a fail safe mode of operation. It is an increasingly popular practice is to have multiple subsystems of partial capacity instead of having just a single equipment. Like if we are providing a single equipment to give us protection complete protection against something. So, instead of having one equipment which is capable of providing complete solution or complete protection, nowadays the reactors are having 2 or 3 or 4 smaller systems, each having say 50% capacity or like that, and having just a single system may lead to catastrophic event, because it may happen at the time of need the system fails, as it may be required to operate very rarely. So, there may not be proper maintenance and the equipment failed at the time of the need. Secondly, unavailability because of maintenance schedule. So, under such situation, so to avoid that we can have multiple subsystems, like having, if we are having 3 or 4 systems with 5% solution, then we are ensuring that adequate backup options are there against single failure, and also some cases even 50% performance is sufficient to address the issue. So, there is no point for all the control rods to get activated. Then comes the term redundancy. It refers to installation of multiple safety systems to achieve a single objective, that is to have perform one kind of safety features, we are installing multiple devices just to ensure. This is something that relates to redundancy, like if our objective is to close this valve, close this pipeline using the valves, these greens are the normal valves. Here you can see instead of one we have put 3 valves, so that at least one of them will operate. So, this is the valve in the closed position. So, if all 3 operates, that is fine, but even if the drive mechanism for the first one and also for the second one fails, we still have a third one. This third valve will operate, or we have to operate this third valve to protect the system. Whereas, when we are looking to have the valves in open situation, then we can put the valve, we have the line in open situation, we want to have the flow, we can put these valves in parallel, and even if at least one of the valve is open, there will be flow through this circuit. So, this is what we call redundancy. In both these cases, just the function that could have been done by a single valve, we are putting 3 valves just to ensure that at least one is operating. The same is referred by the redundancy. In most reactor designs, the several systems are used against the, like the quick reactor shutdown system, or from very fast shutdown system, residual heat removal from core, emergency core cooling, containment isolation, containment heat removal, atmospheric contamination control and cleanup. All this for all these possibilities we have several equipments in the plant. Like you can see in this diagram, this is a similar diagram that I shown out earlier about the physical barriers. Here instead of 4 we are having 6 barriers, like 1, 2 and 3 remains the same, but now we have a concrete shielding around this lattice structure of fuel, and then we have the reinforced concrete shell outside, and then this contamination barrier which was always there. So, we have a refurnished or reinforced rather concrete shell which has been provided to work as additional barrier for safety. CANDU future reactor, I hope you remember the name, Canadian deuterium uranium, which is also the most of the PHWers in India are of CANDU type. So, the CANDU reactor has several essential design features or safety features, like this heat transport system is a safety feature. Under any situation, this heat transport system will provide heat, thereby it can also remove the decay heat if required. Then this is a zoomed view of this particular portion. Here we have these fuel rod bundles which are not able to score, fuel rod bundles which are able to restrict the, or will not able to not allow the fission products to go outside. Then this moderator, in the calandria large volume of moderator are kept, so that can always absorb huge amount of heat. Then this number 5, there is a vault, a concrete vault around this calandria. Then we have a water reserve here which can always be used if some additional heat load is present, and finally the containment chamber. And this is the modified view of these fuel bundles. Here this is the fuel pallet which provides the first layer of barrier. This is another diagram for another reactor. You can see there are additional borating system which can provide additional boron to reduce the reactivity inside the core. We have this emergency core cooling system and residual building. We have the building has been isolated, or building isolation system required the building can be isolated, the emergency feeding system. These are all part of different layers of protection, and these are all mostly to meet those three objectives, that is restricting the reactivity, removing the heat and containing the radioactivity. Next is diversity. It is possible that if all those components used under redundancy are of similar kind, then for the same reason all of them or a particular kind of failure may bypass all of them, which something referred to as the common cause failures, which is an important contributor to our accidents. So, it is for the, if all corresponding equipments are of similar type, then none of them may be able to detect this kind of equipment. That is why we need to use diversity, that is different equipment under the for serving the same purpose can be of different kinds, may have different attributes such as different operating pressures, can have different physical methods of operation like transducer based or mechanical based. The working principle electrical or combustion motor based. Manufacturers can be different for the same equipments, because each manufacturer provides their own features. So, while the equipment broadly is the same, actually there can be quite major differences. Similarly, the design teams, also the same equipment or same system designed by two teams will be having different attributes or different features, thereby ensuring the diversity. This is one schematic or one picture which shows the different kind of action that has been ensured in this Daiichi power station, which falls under both redundancy and diversity. Like the emergency, for emergency safety measure, the short term option, additional deployment of emergency power source vehicle, like what it lost the power. So, they are providing additional power source vehicles. Also, they are providing coastal levees, which is long term objective, and installation of protection walls. In order to secure the power source, they are using the interconnected emergency diesel generator between units, and also inspecting the transmission line towers and measuring an earthquake and tsunami, which is a long term objective. The severe accident measures, deployment of wheel loaders can be an option, but installation of the reactor building, ventilation and hydrogen detectors can be, particularly in BWR type, can be another option. So, for serving the same purpose, we are using different, or we can use different kinds of mechanism, which falls under this diversity. Then initiating event characterization, the reason for which this entire series of events during an accident that happens, it is important to categorize those initiating events as well, because the challenges that can be handled by, what kind of challenges that we are going to face and how that can be handled by using which kind of component or equipment. Then accordingly, the depending upon the initiating event, or most typical categories are like principal effect on potential degradation of fundamental safety functions, which can be increase in heat removal by the secondary side, decrease in heat removal by the secondary side. Similarly, increase or decrease in the flow rate in the coolant system, anomalies in distribution of reactivity and power, decrease in reactor coolant inventory, and reactive release from a subsystem or components. Another principal type can be based upon the initiating event. The control rod malfunction we can have initiated by interfacing loca. Loss of power supply can be another reason. Anticipated system without scram. External events like earthquake and flood, all these are going to have different kinds of effects. Finally, we come to the planned features and design basis. It has been found that all those plants which are based upon the thermal reactors, like the PWRs, BWRs, PHWRs, they have several common features, both from normal operation and safety point of view. Like their source of energy comes from nuclear fission, then they are cooled by some kind of liquid, which is water or heavy water. They continued to generate heat even after shutdown because of the decay heat, which of course keeps on declining with time. Separate systems for cooling the plant in the shutdown state to remove the decay heat. Provisions to cool the reactor core should be normal. Should the normal cooling fail, we must have as backup as emergency core cooling system, and the emergency power systems like diesel generator kind of options if there is a failure of the normal power. So, these are the features that you will find in all the plants, like also confinement to encapsulate radioactive material in the event of an accident. And so, as their design features are quite similar from safety point of view, so we can treat all of them as just a single group, and then we go to the design basis. To define the design basis, the different states of a plant needs to be categorized based upon their frequency of occurrences. First is NO, normal operation, which is the normal startup, operation and shutdown. Next is anticipated operational occurrences, AOO. This refers to the events which are very likely to occur during the lifetime of the reactor. Then design basis accidents, DBA, events which are not expected to occur during the lifetime, but are included for robustness of design and a high level of safety. Finally, design extension conditions, this refers to the large scale accident, quite severe accidents. These are generally hypothetical accidents designed beyond the DBA, which include accidents with significant degradation of the reactor core. The design of the safety and security system should be such that all these classes of plant states can be taken care of by the equipment and procedures within, and the plant operation should remain within the predefined acceptance criteria. If we couple this design basis with the design in depth, then you will find the level 1 is for abnormal operation and failures. The abnormal operation is generally managed by level 2. Abnormal operation means here we revert by AOO. AOO refers to only minor violation from normal operating conditions which are always expected during the life of the plant, and they are generally taken care of by the level 2. You have to remember, NO, the normal operation is not an accident condition, so you do not need any kind of protective layer for that. But the second one, AOO, is taken care of by the second layer, second level. Then DBA are taken care of by level 3, whereas if DEC at all happens, very unlikely, this refers to only very severe situations like in Chernobyl, then we have the level 4 and level 5 if required. Of course, as the level of this accident that goes on, as we move from AOO to the DBA to DEC, the amount of consequences that keeps on increasing, and in certain situations it becomes intolerable. And in this, like just I mentioned, these accidents or this different kind of scenarios in nuclear power plant can also be put in this classifications of accident scenario. Here A1 refers to very minor anomaly, something which actually is taken care of by level 1. Even level, in the second one, this scale 2 incident is also can be taken care of by level 1. Level 3 refers to serious incident, which something in the range of AOO, which can be taken care of by the third layer, and or rather which falls under the scale 3. So, this scale 0 to 3, they falls under this category of incidents. We do not call them accident till this, but once it is above 3, then that is very much an accident. Like 4 is an accident with only local consequences. So, this is where DBA starts to come into picture. 5 is accident with much bigger consequences. 3 Mile Island accident is an example of this level 5, where the reactor core got severely damaged and radioactivity was also released, but that was limited. Level 6 is much serious accident, and level 7 is extremely severe accidents such as in Chernobyl or in Fukushima power stations. In fact, these are the only two examples of level 7 nuclear accidents, and 3 Mile Island is the only major incident to fall under level 5. Level 7 refers to something, a kind of accident which leads to widespread health and environmental effects. So, depending upon what kind of, I should say, when we are in this category, these level 4 and level 5 designs of DID are generally for this, whereas level 1 is capable of taking care of this one itself. This is generally for level 2. Level 3 can take care of this kind of situation, and level 4 and 5 are for larger layers, like level 4 and 5 can take up from this particular point onwards. So, depending upon what kind of accidents happening and several other factors as we have seen today, we can we need to have different kind of safety arrangements, and all those can be defined under those 5 layers of protection. This takes us towards the end of this particular module. So, in module 11 we have seen that any nuclear accident can have severe consequences spanning across generations because of the genetic mutation which it may lead to. The DID is the basic design philosophy which must ensure the protection of human and environment from the harmful effects of radiation. Commonly, DID incorporates 4 layers of physical barriers and 5 layers of protection. Number of physical barriers can be even more, it can be 5 or 6 also, starting from the fuel pellet to the outer containment structure. Failure of one layer of protection must be mitigated by the features of the next layer. 3 fundamental safety function includes the control of reactivity, removal of heat and confinement of reactivity. It is wrong, confinement of radioactivity it should be. Safety features must be fail safe and commonly employs redundancy and diversity in order to increase the stability of this security system. Passive safety features should also come under this category. Initiating event characterization is important to identify the possible safety measures, and finally, the safety system must ensure that the equipment and procedures are available to mitigate the consequences of all classes of plant states within predefined acceptance criteria. So, this takes us to the end of module number 11. Here we have seen different philosophies of reactor safety, modern reactor safety. Generally, design in depth is the main philosophy, which provides or which incorporates 5 layers of protection. We generally would like to restrict the plant up to layer 2 or in the worst case layer 3. Layer 4 is something that corresponds to very severe experience in the level of Chernobyl. There are different ways we can relate the design to this DID concept, like categorizing the initiating effects, categorizing the accident, and several other kinds of situation categorization as well. But overall, a plant must strictly adhere to these design philosophies in order to ensure the utmost protection of human being and also the environment against any kind of ionizing radiation. So, thank you very much for your protection. Keep posting your comments. I shall be very happy to respond to your queries, and we have just one more week to go in this particular course. So, see you in the next week. Bye.